In the vastness of the universe, where galaxies spin like silent whirlpools of light, and time itself seems to flow in waves, there exists a mystery so powerful that even light cannot escape its grasp. This is the story of the black hole. Imagine a place where gravity bends space as if it were a sheet of rubber, pulling everything inward endlessly without release. A place where the rules we know on Earth, speed, distance, even the passing of seconds, are stretched and twisted until they no longer resemble the laws we trust. Our journey begins with a simple question. Can a black hole swallow light itself? At first, the idea seems impossible. Light, after all, is the fastest thing we know, racing through the cosmos at 300,000 kilometers every second. Nothing outruns it, nothing slows it down. Yet, black holes are not ordinary objects. They are cosmic traps born from stars that collapse under their own weight, compressing all their mass into a single point of infinite density, a singularity. Surrounding this singularity is a boundary we call the event horizon. Cross this boundary, and not even light can return. To understand this, we must follow the path of light itself. Picture a beam escaping from the surface of a star, its photons traveling straight and true. In ordinary space, they would spread forever, carrying warmth and illumination to distant corners of the cosmos. But near a black hole, space is no longer ordinary. According to Einstein's theory of relativity, massive objects curve space-time around them, and a black hole is mass beyond measure. For light, which always moves along the curves of space, the path bends inward until it loops back, swallowed by the horizon. The black hole doesn't chase the light. It simply reshapes the stage on which light tries to flee. This story will take us deep into that invisible frontier. We will explore how black holes are formed, why they can capture even the fastest travelers of the universe, and what mysteries lie hidden just beyond the horizon. Through analogies, vivid examples, and guided imagination, we will step closer to understanding how something so dark can teach us so much about the nature of reality itself. Chapter 2: The Event Horizon. The point of no return. Imagine you are an explorer sailing across the cosmic ocean. Ahead lies a dark whirlpool unlike any storm you have ever faced. Its edges appear calm at first, but closer inspection reveals a terrifying truth. Beyond a certain boundary, the current becomes so powerful that no ship can turn back. Cross that invisible line, and you are gone forever. This is the essence of the event horizon, the most famous feature of a black hole. It is not a physical surface like the crust of a planet or the blazing surface of a star. Instead, it is a boundary in space-time itself, a limit that separates the knowable from the unknowable. Let's think of it more carefully. According to Einstein's general theory of relativity, gravity is not a force pulling object from a distance, but rather the curvature of space-time caused by mass and energy. Light, though massless, still follows the curves of this cosmic fabric. Near Earth, those curves are gentle. Near a black hole, they are steep. At the event horizon, they become so steep that all possible paths lead inward. To an outside observer, the event horizon appears as a perfectly black sphere. If light cannot escape, then no information can cross outward. Anything falling in, matter, radiation, even time itself, becomes trapped. The horizon is the last message the universe receives before silence. But here's a paradoxical beauty. While nothing escapes from inside, the horizon itself can glow in extraordinary ways. Gas and dust spiraling toward the black hole form an accretion disk, heating to millions of degrees as friction tears them apart. This disk shines brightly in X-rays and visible light, making the region around the event horizon one of the most luminous in the universe. The darkness of the hole is framed by the brilliance of its victims' final screams. To make this more relatable, imagine a waterfall. A fish swimming near the top can escape if it paddles hard enough. But as the fish drifts closer to the edge, the current grows stronger. At some point, no matter how fast the fish swims, it cannot resist being carried over. The cliff's edge is the fish's event horizon. Beyond it, the plunge is inevitable. Time, too, behaves strangely at the event horizon. To the falling traveler, nothing seems unusual. They pass through without noticing, continuing their descent toward the singularity. But to a distant observer, watching from far away, the traveler never quite reaches the horizon. Instead, they appear to slow, fading into darkness, their light stretched into longer and longer wavelengths until it vanishes. To us, the traveler freezes in time at the horizon, a ghost image forever suspended at the edge of eternity. This is not merely science fiction. It is the prediction of relativity. Space and time themselves warp in the presence of extreme gravity. The horizon is where this warping becomes absolute, where the future of any object is sealed. And yet, mysteries remain. Is the horizon truly the end? Quantum physics suggests a different story. Tiny fluctuations in the vacuum may allow information to leak out in the form of Hawking radiation, a faint glow of particles slowly evaporating the black hole. If this is true, the event horizon is not only a boundary of silence, but also a slow whisper of destruction. For now, though, we stand on the outside, gazing at the ultimate wall between what can be known and what lies forever hidden. The event horizon is the curtain of the greatest cosmic theater, a stage we can watch but never enter. Chapter 3. Time and light in the grip of gravity. If black holes are the sculptors of space, then they're also the masters of time. Near their dark horizons, not only is light captured, but the very rhythm of the universe begins to twist. Let's begin with light itself. To us, light seems untouchable, always racing at the same speed, always reliable. You flick on a flashlight, and the beam cuts instantly through the darkness. But remember, light does not travel in a straight line through an empty void. It follows the curves of space and time. Where space-time bends, so too does light. This is why starlight passing near the sun bends slightly, an effect first observed during a solar eclipse in 1919. That single observation confirmed Einstein's prediction and revealed that gravity could act not just on matter, but on light itself. If the sun could bend starlight by a fraction of a degree, imagine what a black hole could do. Near a black hole, light does not merely bend. It orbits. Photons can be trapped in a delicate dance around the black hole in what scientists call the photon sphere. Here, light circles endlessly, balanced between freedom and capture. But this balance is fragile. A tiny nudge inward, and the photon plunges past the event horizon, gone forever. A tiny nudge outward, and it escapes, spiraling away into space. Now consider time. Time feels absolute in our daily lives. 1 second follows another, minutes pass, hours march forward with regularity. But time is not universal. It is woven into the same fabric as space. Where gravity is strong, time itself slows. This is not an illusion, but a measurable effect. Astronauts orbiting Earth age fractions of a second less than those on the ground because they experience weaker gravity. Around a black hole, this effect becomes profound. To a distant observer, someone approaching the event horizon appears to move slower and slower, their clock ticking more gradually, their heartbeat stretching into eternity. As they fall, their light shifts to redder and redder wavelengths, fading until it disappears completely. Yet for the falling traveler, time feels normal. Their watch ticks at the same pace. They see themselves moving forward as always. This contradiction is one of the strangest lessons of relativity. Time does not flow the same for everyone. Near a black hole, the difference becomes so extreme that the two perspectives cannot be reconciled in ordinary human terms. Imagine standing safely far from the black hole, watching a friend fall in. You would never actually see them cross the horizon. To your eyes, they freeze at the edge, dimming into invisibility. Meanwhile, from their perspective, they glide across effortlessly, heading toward the singularity. Two truths coexist, each valid in its own frame of reference. This warping of time gives rise to remarkable possibilities. In theory, one could orbit near a massive black hole, experiencing hours while centuries pass in the outside universe. Black holes could thus become natural time machines, carrying travelers into the far future simply by holding them near their gravitational grip. And so, in the presence of a black hole, light bends, time stretches, and reality itself feels like a tapestry pulled too tight, its threads distorted. These are not just curiosities for astronomers. They're profound demonstrations of how deeply interconnected space, time, and gravity truly are. Chapter 4: The Dance of Matter. Accretion disks and cosmic jets. When we picture a black hole, we often imagine a lonely, dark sphere floating silently in space. But in reality, black holes are rarely so quiet. Most of them live in environments filled with gas, dust, or even entire stars wandering too close. And when matter approaches the abyss, the story becomes spectacular. Imagine a star drifting near a black hole. Its outer layers feel a growing pull, stretched by tidal forces so extreme that the star begins to tear apart. Gas from its surface spirals inward, forming a swirling whirlpool of matter around the black hole, the accretion disk. This disk is no ordinary structure. As gas falls inward, it crashes against other streams of gas, heating to millions of degrees. Friction and compression cause it to blaze with energy, glowing brightly in X-rays and ultraviolet light. To distant telescopes, these disks shine with a brilliance that can outshine entire galaxies. Paradoxically, the darkest objects in the universe are often surrounded by the brightest displays of light. But the drama does not end there. As matter spirals closer, magnetic fields twist and snap within the disk. These tangled lines of force act like cosmic catapults, channeling some of the infalling material away from the black hole. Instead of being swallowed, the matter is accelerated outward in narrow beams, moving at nearly the speed of light. These are the relativistic jets, titanic streams of plasma that can stretch for thousands, even millions of light years across space. Picture a lighthouse, but on a scale that dwarfs galaxies. These jets cut through interstellar space, carrying energy from the very edge of the black hole out into the universe. They ignite regions of gas far away, sculpting the structure of galaxies and influencing the birth of stars. In this sense, black holes are not merely destroyers. They are also creators, shaping the evolution of the cosmos itself. To understand the accretion disk, think of a pot of boiling water. The heat makes the water churn violently, with bubbles rising and bursting. In a similar way, the gas in the accretion disk churns under unimaginable pressure, glowing hotter the closer it gets to the event horizon. But unlike boiling water, this cosmic cauldron does not simmer quietly. It radiates energy with a ferocity that can be detected across billions of light years. Astronomers use this glow to locate black holes. Since the hole itself cannot be seen, the disk and jets act as cosmic signposts. When we see X-ray bursts or enormous jets extending into space, we know a black hole lurks at the center. The most extraordinary example of this dance is found in quasars, galactic cores powered by supermassive black holes. Quasars are so luminous that they can be seen across the visible universe, shining brighter than the combined light of all the stars in their host galaxy. They are engines fueled by accretion, where gravity's hunger is converted into radiant power. And yet, through all of this spectacle, a strange irony remains. No matter how brightly the disk burns, no matter how far the jets stretch, the central black hole itself stays invisible. All the light we see comes not from within, but from the doomed matter desperately resisting its final plunge. In this way, black holes embody contradiction. They are cosmic prisons of light, yet they also give rise to some of the most radiant phenomena in the universe. They swallow, and yet they shine. They destroy, and yet they shape creation. Chapter 5: Windows of Observation. How we see the invisible. How do you study something that cannot be seen? This is the great challenge of black holes. They emit no light, no radiation that we can catch directly. They hide behind a curtain of darkness beyond the reach of our eyes. Yet, the history of science shows us that humans have always found ways to glimpse the unseen. In the 20th century, astronomers began to notice stars behaving strangely. Some stars orbited nothing, tugged around empty space as if by an invisible partner. Others flared in bursts of X-rays, as if something unseen was tearing matter from their surfaces. These signs hinted at the presence of black holes long before we had the tools to capture their image. The first step in observing black holes is indirect. We watch their influence. We measure the orbits of nearby stars, the glow of hot accretion disks, the thunder of cosmic jets. From these clues, we infer the hidden giant at the center. One of the most stunning examples lies in the heart of our own galaxy, the Milky Way. For decades, astronomers tracked stars dancing around an invisible point near Sagittarius A star. Their motions revealed an object with a mass millions of times greater than the Sun, yet occupying a space no larger than our solar system. Nothing but a supermassive black hole could explain such density. But the true breakthrough came in 2019, when humanity achieved the impossible. We captured the first direct image of a black hole shadow. It was the work of the Event Horizon Telescope, EHD. Not a single telescope, but a network of observatories spread across the globe, from the mountains of Chile to the frozen plains of Antarctica. By linking them together through a technique called very long baseline interferometry, scientists created an Earth-sized telescope capable of resolving details smaller than the eye of a needle held on the moon. They aimed this colossal eye at the galaxy M87, 55 million light years away. And in April 2019, the world saw it, a glowing ring of fire surrounding a dark center. The image was blurry, rough like a fingerprint pressed into the fabric of space. But it was enough. The black silhouette in the middle was the shadow of a black hole, the first direct evidence that Einstein's vision of warped space-time was real. For the first time, we did not just believe. We saw. The significance was profound. Humanity, a species that once mapped the heavens with naked eyes, had now captured the image of a place where light itself perishes. That shadow told us not only that black holes exist, but that our theories of gravity held true even in the most extreme realms. Since then, the EHD has given us more glimpses. Most recently, the image of Sagittarius A*, the black hole at the center of our Milky Way. Though fuzzier than M87*, it confirmed what decades of observations had suggested. We live in a galaxy bound by a hidden heart of darkness. And yet, even as we refine our vision, black holes remain mysterious. Each observation is a window, but the view is always partial. We see the glowing matter around them, not the singularity itself. We measure the shadow, not the core. Like shadows on a wall, our knowledge is real but incomplete. Still, the pursuit is relentless. With better telescopes, sharper images, and new technologies, we hope to uncover more. Perhaps one day, we will witness the dance of photons in the photon sphere or capture the final flicker of a black hole evaporating into nothingness. Until then, the images we hold are more than science. They're symbols of human curiosity, proof that even in the darkest corners of the universe, we find a way to shine a light. Chapter 6: The Paradox of Hawking Radiation. When black holes shine for centuries, black holes were imagined as the ultimate prisons of the cosmos, dark abysses from which nothing, not even light, could escape. They were one-way doors into oblivion, eternal and unchanging. But in the 1970s, a young physicist named Stephen Hawking proposed an idea so radical that it reshaped our understanding of black holes forever. Hawking asked a simple but daring question: what happens when we bring the laws of quantum mechanics to the edge of a black hole? To answer, we must first step into the strange world of quantum physics, where emptiness is never truly empty. What seems like a vacuum, devoid of all matter and energy, is actually a restless sea of activity. Tiny pairs of particles and antiparticles constantly pop into existence, only to annihilate each other in a blink, restoring the void. This phenomenon is called quantum fluctuation. Now, imagine such a pair forming right at the edge of a black hole's event horizon. Normally, the two would collide and vanish as usual. But what if one particle falls into the black hole while the other escapes? The one that escapes becomes real, detectable energy radiating away from the black hole. The one that falls inward carries negative energy, effectively reducing the mass of the black hole itself. This is Hawking radiation, a faint glow of particles leaking from the very boundary of the event horizon. Paradoxically, it means black holes are not completely black. They shine, ever so slightly, with a whisper of quantum fire. The consequences of this idea are staggering. If black holes radiate energy, they must eventually lose mass. Over immense timescales, far longer than the current age of the universe, black holes will evaporate completely. The titans of darkness are not eternal. They are mortal. Given enough time, even the largest supermassive black hole will fade into nothing. This revelation shattered the old view of black holes as permanent tombs. Instead, they became dynamic objects with lifespans. It also raised a haunting question: what happens to the information that falls into a black hole? In physics, information is sacred. It tells us about the state of matter, the arrangement of particles, the details of a system. If a black hole evaporates and vanishes, what happens to the information it swallowed? Is it destroyed forever? Hawking initially argued yes, information is lost. But this idea clashed with the foundations of quantum theory, which insists that information can never truly disappear. This conflict gave birth to the black hole information paradox, one of the greatest unsolved mysteries in modern physics. Entire generations of scientists have debated it, proposing bold solutions. Maybe the information is encoded in the Hawking radiation. Maybe it is stored on the surface of the event horizon like a cosmic hologram. Maybe space-time itself preserves it in ways we do not yet understand. Regardless of the answer, Hawking radiation transformed black holes from cosmic endpoints into cosmic storytellers. Instead of eternal silence, they offer us a faint voice, a signal that even in darkness, physics is at play. To imagine it, picture a giant block of ice slowly melting under the sun. Though immense, it cannot resist the slow, steady loss of mass. In the same way, a black hole radiates away, imperceptibly to us now, but inevitable in the grand timeline of the cosmos. This is the paradox. Black holes, the very symbol of inescapable gravity, are also fragile. They burn away not in fire, but in whispers. And those whispers might hold the key to reconciling the two great pillars of science, Einstein's relativity and quantum mechanics, into one deeper truth. In the end, Hawking's insight reminds us that nothing in the universe is absolute. Not even the darkest night lasts forever. Chapter 7: The Information Paradox. Secrets at the edge of physics. Black holes have always stood as guardians of mystery, but none of their riddles is more confounding than the information paradox. At its heart lies a simple but devastating question: what happens to the information about matter that falls into a black hole? Let us pause to clarify what information means in physics. It is not just words in a book or files on a computer. Information is the fundamental description of a universe. The spin of a particle, the arrangement of atoms, the exact state of a system. According to the laws of quantum mechanics, this information can never truly vanish. It may change form, it may become scrambled beyond recognition, but it cannot be erased. Yet black holes seem to defy this principle. Imagine tossing a book into fire. The pages burn, the letters vanish, but the information is not destroyed. It is carried away by the smoke, the ash, and the light. In theory, if you had perfect knowledge of every particle of smoke and heat, you could reconstruct the words of the book. Destruction in the everyday sense is only transformation at the quantum level. Now, imagine tossing that same book into a black hole. The paper, the ink, the words, every atom plunges past the event horizon. From the outside, nothing emerges. Over billions of years, the black hole itself evaporates through Hawking radiation. If the hole completely disappears, what remains of the book's information? If the information is truly lost, then quantum mechanics, our most successful theory of the microscopic universe, collapses. If the information survives somehow, then it must be encoded in a way we do not yet understand. This is the paradox, a tension between two pillars of physics, general relativity and quantum mechanics. Hawking initially believed information was destroyed. It was a bold statement, but one that shook the scientific community. If true, it meant physics was incomplete. Yet others, including physicists like Leonard Susskind and Gerard T. Hooft, argued fiercely against this idea. The result was a decades-long battle known as the Black Hole War. From this war arose radical ideas. One is the concept of the holographic principle. It suggests that all the information inside a volume of space can be described on its boundary surface, much like a hologram encodes a 3D image in 2D light. Applied to black holes, it implies that the event horizon itself stores every detail of what has fallen in, etched onto its surface in a cosmic code. The black hole, then, is not a vault that erases information, but a library with walls that write in invisible ink. Another idea is that Hawking radiation itself carries the hidden information, though scrambled and nearly impossible to decode. In this view, the faint glow from a black hole is not random. It is a message written in the language of quantum physics, waiting for us to decipher. More recently, theories involving wormholes and quantum entanglement suggest even stranger possibilities. Information may be preserved in connections across space-time, linking the inside of the black hole with the outside universe in ways that challenge our intuition. But the paradox is not just a technical puzzle. It is a reminder of the limits of human understanding. For the first time, we face a place where our two great theories, relativity and quantum mechanics, contradict each other. To resolve the paradox, we may need a deeper theory, a theory of everything that unites the cosmic and the quantum. Standing at the edge of a black hole, then, is like standing at the edge of knowledge itself. We peer into the darkness, not only to understand the whole, but to glimpse the future of physics. The answer to the paradox may reveal not just the fate of information, but the very architecture of reality. And so the black hole, once thought to be the universe's dead end, becomes instead its greatest question mark. Chapter 8: Black Holes and the Fabric of the Universe. Dark architects of galaxies for much of history, black holes were imagined as monsters lurking in the dark, feeding on stars and devouring light. But as our telescopes grew sharper and our theories deeper, a new picture emerged. One in which black holes are not just cosmic predators, but cosmic architects. At the center of nearly every large galaxy, including our own Milky Way, lies a supermassive black hole. These giants contain millions, sometimes billions, of times the mass of our sun Sagittarius A*. The black hole at the heart of the Milky Way has a mass equivalent to about 4 million suns, compressed into a region smaller than the orbit of Mercury. For decades, astronomers wondered, how could such titans form, and what role do they play in the life of galaxies? The answer surprised us. Black holes are not passive passengers in galaxies. They're central to their growth and evolution. The galactic heartbeat consider a galaxy as a vast city of stars. In the bustling center sits the black hole, silent but powerful. Around it, stars whirl like dancers caught in its invisible gravity. Gas clouds drift inward, feeding the black hole and igniting the glow of accretion disks. Jets shoot outward, pumping energy back into the galaxy. This energy is not wasted. It sculpts the shape of the galaxy itself. When a black hole consumes too much matter. It can unleash such powerful jets and winds that it pushes gas away from the galactic core. Without gas, stars cannot form. In this way, the black hole acts as a regulator, deciding when new generations of stars are born and when the galaxy rests in silence. Quasars, beacons of the early universe, the most dramatic examples of this process are quasars. Billions of years ago, young galaxies fed their black holes at furious rates. Accretion disks blazed so brightly that quasars became the most luminous objects in the cosmos, visible across unimaginable distances. These ancient lights tell us that supermassive black holes were already active when the universe was still in its infancy, shaping galaxies from the very beginning. Without black holes, galaxies might grow too quickly or collapse chaotically under their own weight. With them, galaxies evolve with structure and rhythm. In this sense, black holes are like gardeners, pruning, trimming, and guiding growth, not by design, but by the natural laws of physics. A dance of creation and destruction, it is tempting to see black holes as destroyers, but their influence is double-edged. By swallowing matter, they prevent galaxies from becoming overcrowded with stars. By expelling energy through jets, they trigger star formation in distant clouds, sparking life where there was only darkness. In this way, black holes are paradoxical beings. They are born from death, they feed by destruction, and yet they sustain creation on a cosmic scale. Our place in the pattern, and here lies a humbling truth. Without black holes, we might not be here at all. The elements that make life possible, carbon, oxygen, iron, were forged in stars and distributed by supernovae. But the conditions that allowed galaxies to nurture such stars, to recycle matter in cycles of birth and death, were shaped by the presence of black holes. When we look up at the night sky, the twinkling of every star is in some sense a story written under the guidance of these dark architects. Chapter 9: Black Holes and Time Travel. The dreams of science fiction since the moment black holes entered popular imagination. They have been more than astronomical objects. They became gateways, portals into other worlds, other times, even other universes. In science fiction, black holes are not just the end of the road, but the beginning of adventure. Time dilation. The real science behind the myth, the seed of these ideas, lies in Einstein's theory of relativity. Near a black hole, time slows compared to the outside universe. This is not fantasy, it is measurable science. We know astronauts orbiting Earth already age slightly slower than people on the ground. Take that effect to the extreme, and you have the foundation of time travel into the future. Imagine orbiting just outside the event horizon of a supermassive black hole. For you, only a few hours pass. But for someone far away, decades or even centuries might unfold. When you return, you step into a future you have skipped, as if the black hole itself were a time machine. This idea was beautifully captured in the film Interstellar, where astronauts visiting a planet near a black hole experience hours, while years pass for their colleagues waiting in orbit. Though dramatized, the principle is grounded in real physics. Wormholes, the bridges of imagination, but time travel in stories often goes beyond this. What if black holes could also lead elsewhere? Physicists have long speculated about wormholes, shortcuts through space-time that connect distant points, like tunnels piercing through the cosmic fabric. In theory, the intense curvature near a black hole could form such bridges. If one end of a wormhole sits near a black hole, and the other somewhere else in the universe. Stepping in could mean emerging light years away in an instant. Push the idea further, and wormholes could even connect different times, not just different places. A black hole might not be only a trap, but a gateway, though one guarded by forces so violent that survival seems impossible. Science fiction and the human dream from novels to films. Black holes have been imagined as portals to higher dimensions, gateways to rebirth, or pathways to civilizations beyond the stars. They embody both fear and hope, fear of annihilation, hope of discovery. Yet, reality humbles us. Current physics tells us wormholes, if they exist, are unstable. They would collapse before anything could pass through. Some theories suggest exotic matter with negative energy could hold them open, but such matter has never been observed. Still, science fiction serves a purpose. It fuels curiosity, inspiring generations of scientists to ask, what if? And sometimes, what begins as fiction becomes science. The frontier of the unknown, even if wormholes never exist. Black holes remain gateways in another sense. They are gateways of knowledge, pushing us to the limits of physics. To study them is to brush against the edges of time, causality, and the nature of existence itself. For now, black holes keep their secrets, but they remind us of something deeply human. Our longing not just to survive, but to explore, to cross thresholds into the unknown, to imagine that behind every horizon lies another story. Chapter 10: Black Holes and the End of the Universe. A journey into the far future, let us imagine time stretched far beyond human history, beyond the fall of civilizations, beyond the life of stars, beyond even the galaxies as we know them. The universe, once young and vibrant, will one day grow old. And in that distant twilight, black holes will remain as the last titans of existence. The era of stars today, we live in the stelliferous era, an age where stars blaze across the cosmos, galaxies swirl in majestic spirals, and life finds warmth under the glow of suns. But this era is only a chapter. Stars burn their fuel relentlessly, and in trillions of years, even the smallest red dwarfs, the longest-lived stars, will flicker out. As stars die, galaxies grow dim. The night sky, once filled with billions of suns, will fade into darkness. The black hole era, when the stars are gone, what remains? Planets, stellar remnants, and above all, black holes. They will dominate the cosmos. Stellar mass black holes from collapsed stars, supermassive black holes anchoring the hearts of dead galaxies. They will be the giants left standing in a cold and fading universe. But even these titans are not eternal. Hawking radiation ensures that black holes slowly leak energy. Though the process is unimaginably slow, the clock is ticking. Small black holes evaporate first, disappearing in flashes of radiation. Larger ones last longer. The supermassive black holes, weighing billions of solar masses, will endure for perhaps 10 years, a span so vast it dwarfs comprehension. Yet even they, in the end, will shrink, dim, and vanish into nothing. The heat death of the universe after the last black hole evaporates. The universe enters its final stage, heat death. With no stars, no black holes, and no organized structures, all that remains is a thin soup of particles and radiation, spread so evenly across space that no change, no event, no story can ever unfold again. Entropy will have reached its maximum. The universe, once alive with galaxies, quasars, and light, will fall silent forever. A cosmic perspective, it is a sobering thought. Everything we know, from the dance of galaxies to the spark of life, is temporary. Even the mighty black holes, those cosmic abysses that swallow light, are themselves subject to time's relentless tide. And yet, there is beauty in this story. To recognize that the universe has an ending is to appreciate the fragility of its present. Every star in our night sky, every photon that reaches our eyes, shines against the backdrop of an inevitable darkness. The fleeting makes the moment precious. The last fireworks, some physicists suggest the final evaporation of black holes might not be quiet. As the black hole shrinks to microscopic size, it could release a sudden burst of energy, like a final scream before vanishing. These black hole fireworks could light up the cold universe one last time. If so, the universe's final act may not be silence, but a storm of sparks. The human place in the far future, though our species will be gone long before such epochs arrive, our minds today can journey there in thought. In contemplating the far future of black holes, we glimpse both our smallness and our greatness, small in time and space, yet great in imagination. To think about the end of the universe is itself an act of defiance, proof that while stars and black holes will one day vanish, curiosity endures as long as there are minds to ask questions. Chapter 11: The Human Connection, Black Holes in Culture, Myth, and Imagination. Since ancient times, humans have looked into the night sky and filled the darkness with meaning. Long before telescopes, we wove myths of gods and monsters into the constellations. The sky was not empty. It was a mirror of our fears, our hopes, and our questions. So it is with black holes. Though discovered through the language of mathematics and confirmed by physics, they resonate with us far beyond science. They are more than astrophysical objects. They are symbols, echoes of themes that have haunted human imagination for millennia. Darkness as a symbol in myth and poetry. Darkness is often the unknown, the underworld, the abyss, the shadow that hides both danger and possibility. Black holes embody this archetype perfectly. They are the literal darkness that no light escapes, the cosmic abyss into which all paths may vanish. To some, they represent death, the final end, the swallowing void. To others, they are rebirth, gateways to other worlds, reminders that destruction and creation are intertwined. Black holes in stories and art science fiction seized upon black holes almost as soon as they entered the scientific lexicon. From early pulp novels to modern cinema, they are painted as portals, doomsday engines, or mysterious bridges. Films like Interstellar do not simply show black holes as physics problems, but as emotional crucibles, places where human love, sacrifice, and hope are tested against the backdrop of cosmic infinity. Artists, too, find inspiration in their imagery. The swirling accretion disk, the blazing jets, the central shadow, they are both terrifying and beautiful. Painters and musicians have evoked the black hole as a metaphor for grief, obsession, or longing. To fall into one is to surrender, to be consumed, to be transformed. Philosophical reflections, philosophers see black holes as metaphors for the limits of knowledge. Just as nothing escapes the event horizon, no information from beyond it can reach us. Is the ultimate boundary of understanding, a reminder that some truths may forever lie beyond our grasp. Yet, Paradoxically, black holes also represent the drive to know, because the very existence of this boundary tempts us to approach it. They also provoke reflections on time and mortality. If a black hole can slow time, if it can outlast stars and galaxies, then what does that say about our fleeting lives? In contemplating them, we confront not just cosmic fate, but our own. The inner black holes, there's another reason black holes speak to us. They mirror our inner worlds. Everyone carries moments of darkness, of loss, of despair that seem inescapable. The metaphor of the black hole becomes deeply personal. To fall into one is to face the parts of ourselves that feel beyond hope. And yet, in physics, black holes are not eternal. They evaporate, they end. Perhaps, in that, we find a lesson. Even the deepest shadow does not last forever. From myth to science, and back again, the journey of black holes is the journey of humanity itself. From mythic abysses to mathematical predictions, from invisible speculation to direct imaging, we have turned symbols into science. And yet, even as we measure their masses and map their shadows, they return to us as symbols once more, reminders of mystery, mortality, and wonder. In the end, black holes are not only out there in the cosmos. They live in our stories, our art, our fears, and our dreams. They remind us that the universe is vast, but also the human imagination is vast enough to meet it. Chapter 12, Toward a Theory of Everything. Black holes as keys to physics for over a century. Two great pillars have supported the edifice of modern physics: Einstein's general relativity and quantum mechanics. Each is a masterpiece. Relativity describes the vast, the massive, the cosmic. It tells us how space and time bend under gravity, how stars orbit, how galaxies evolve. Quantum mechanics rules the small, atoms, particles, the strange dance of probability that underlies reality itself. Both theories are stunningly accurate in their domains. And yet, like two maps drawn of the same land but never aligning at the edges, they refuse to join. Wherever gravity becomes as strong as the quantum, the heart of a black hole, the first moments of the Big Bang, our equations break. Black holes as natural laboratories, black holes are not just mysteries, they're laboratories. They push matter, energy, space, and time to conditions no human experiment can reproduce. In their depths, relativity and quantum mechanics collide. The singularity predicted by relativity, a point of infinite density, screams of incompleteness. Quantum mechanics, which thrives on uncertainty and fluctuations, insists such infinities are unphysical. Somewhere beyond our current knowledge lies a deeper law, one that reconciles these two visions. Quantum gravity. The missing piece, the quest for this deeper law, is often called the search for quantum gravity. It is the holy grail of physics, the long-sought theory of everything. One approach is string theory, which imagines that all particles are not points but tiny vibrating strings, their harmonies giving rise to the particles we see. String theory naturally incorporates gravity and suggests that space-time itself may emerge from more fundamental ingredients. In this framework, black holes are not paradoxes but playgrounds, where strings weave together geometry and quantum rules. Another approach is loop quantum gravity, which suggests space itself is quantized, built from discrete chunks like the pixels of a cosmic screen. At the singularity, instead of infinite density, space-time may bounce, avoiding the paradox entirely. The holographic universe, perhaps the most tantalizing idea, is the holographic principle born from black hole physics. It suggests that the entire universe could be described not by its volume, but by information written on its boundary, like a hologram encoding a 3D image on a 2D surface. If true, our reality may be a projection, and black holes are the clearest proof. Their horizons appear to encode information about everything that falls in, hinting that the surface of the universe may hold its deepest secrets. Black holes as bridges to the future of science. To solve the puzzles of black holes is to solve the puzzle of existence. Are space and time continuous or granular? Is information truly preserved, or can it vanish? Are black holes singularities or doorways to deeper layers of reality? Every breakthrough brings us closer, but the full theory still eludes us. What we know is this: black holes are not just endpoints of stars. They are pathways to new physics, to unifying the cosmic with the quantum, to glimpsing the architecture beneath reality itself. The human dream of unity in the end, the dream of a theory of everything, is not just scientific, it is human. We long for unity, for simplicity beneath the complexity, for a single story that makes sense of the cosmos. Black holes, in their silence, may hold that story. Perhaps one day, when the equations finally align, we will look back and realize that the darkest places in the universe were not barriers, but keys that unlocked the deepest truth of all. Chapter 13: Facing the Abyss. The human future with black holes. From the first time humans looked at the night sky, we have been explorers. We crossed oceans, mapped continents, and finally stepped into space itself. Yet before us lies the greatest frontier of all, the black holes that dot our galaxy like silent sentinels. Harnessing the dark giants, could we one day use black holes? Some scientists imagine it. The accretion disks around black holes release staggering amounts of energy, far beyond anything a star can provide. If a future civilization could tap into this energy, it would possess a power source capable of sustaining not just worlds, but entire empires among the stars. Others speculate about black holes as engines for interstellar travel. A rotating black hole, according to theory, might bend space-time in ways that allow shortcuts, perhaps even stable wormholes. If so, black holes could become the ultimate cosmic gateways, though the dangers are beyond anything we know. The danger and the wonder, of course, the risks are immense. To stray too close is to face spaghettification, the stretching of matter into thin strands by tidal forces. To fall past the horizon is to vanish forever from the known universe. Black holes are not gentle companions. They are extremes of reality. And yet, humans have always danced with danger in the pursuit of knowledge. The very act of approaching a black hole would be the pinnacle of exploration, our ship sailing not just into space, but into the very nature of space-time itself. A mirror for humanity. In truth, black holes are more than destinations. They are mirrors. They reflect our deepest fears, the fear of nothingness, of loss, of limits. But they also reflect our greatest strengths, the courage to face the unknown, the imagination to dream beyond horizons, the will to seek meaning in the silence of the cosmos. One day, if we survive long enough, our descendants may stand on the edge of a black hole and gaze into its dark heart, not with fear, but with wonder. And in that moment, they may understand that the abyss is not an end, but a beginning. Epilogue. Light in the darkness, our journey began with a question: can a black hole swallow even light itself? The answer, we discovered, is yes. And yet, the story is far richer than that. Black holes are not mere destroyers. They are sculptors of galaxies, regulators of stars, paradoxes of physics, symbols of mystery, and perhaps even engines of creation. They trap light, but they also inspire it. Light from accretion disks, light from jets, light from the minds of those who dare to study them. In the end, the true power of black holes is not only in their gravity, but in their ability to stretch our imagination. They remind us that the universe is vast beyond comprehension, and that we, small as we are, have the courage to look into the dark and ask questions. Perhaps that is the greatest lesson of all. Even in the deepest shadow, curiosity is a kind of light. And as long as we carry it, no darkness, not even that of a black hole, can swallow us whole.